Welcome to another lecture of electronic devices and circuits, in which we'll discuss feedback amplifiers. Proceed ahead with the previous lecture. So, a typical feedback connection, which is shown over here, you can see from here. The input voltage, input signal, that is Vs, is applied to the mixer network, where it is combined. This is the mixer. It is combined with the feedback signal. Here is the feedback signal. Now this is the amplifier. We are giving the input at amplifier. We are getting the output, and the output is given with the feedback. And feedback. So the input to the feedback is the output voltage, and output of the feedback is Vf. So Vf upon V0 will be the feedback gain, and here V0 upon V input will be the forward path gain. So the difference of these signals, Vi, is then the input voltage to the amplifier. The difference of these two will be the difference voltage to the amplifier. A portion of the amplifier output VO is connected to the feedback, which provides a reduced portion of the output as feedback signal is applied to the mixer network. So if the feedback signal is of opposite polarity to the input signal, it is negative feedback. Although negative feedback results in reduced overall voltage gain, a number of improvements are obtained because of the negative feedback. Higher input, the input impedance increases 1 plus A beta times. A is the forward gain and beta is the feedback gain. Better stabilized voltage gain, improved frequency response. The frequency also increases 1 plus A beta times. Lower output impedance, reduced noise, and more linear operation. So there are 4 basic ways of connecting the feedback signal. Both voltage and current can be fed to input either in series or in parallel. So voltage series feedback, voltage shunt feedback, current series feedback, and current shunt feedback. So voltage refers to the connecting the output voltage as input to the feedback network. Current refers to tapping of some of the output current through the feedback network. Series refers to connecting the feedback signal in series with the input voltage. Shunt refers to the connecting the feedback signal in shunt with the input voltage. So here are the 4 topologies shown over here. You can see this is the voltage series feedback. The output voltage is taken and connected to the in series with the input voltage. Second is the voltage shunt. You can see the output voltage is given as a shunt in parallel with the input. And here IF is nothing but beta into V0, where beta is equal to IF upon V0. Third one is the current series. You can see this is current series. We are taking the current at the output and providing the current at the input. Here the gain is I0 upon Vi, and here it is Vf upon I0. And fourth one is the current shunt feedback. We are taking the current at the output. We are giving current as input to this feedback, and we are getting the current at the output, and we are giving it to the. So current, voltage series, voltage shunt, current series, and current shunt feedback networks. 4 topologies. Series feedback connections tends to increase the input resistance, whereas shunt connection tends to decrease the input resistance. Voltage feedback tends to decrease the output impedance, where the current series tends to increase the output impedance. Typically, higher input and lower output impedances are desired for cascade. Most of the electronic and electrical circuitry, if you are cascading it, connecting with other network, high input impedance and low output impedance is desirable in all the cases. So both of these are provided using the voltage series feedback connection. We shall therefore concentrate first on this amplifier connection. Gain with feedback. So we'll examine the gain. The gain without feedback is A, is that of amplifier stage. With the feedback B, the overall gain of the circuit is reduced by factor 1 plus AB times. A summary of the gain and feedback factor will be seen. You can see in a tableized format it has been shown. For all the 4 configurations, that is voltage series, voltage shunt, current series, and current shunt. So gain without feedback here is A, feedback for feedback path is beta, and gain with feedback is AF. So for voltage series, the gain without feedback is V0 upon Vi. For the voltage shunt, V0 upon II, and current series I0 upon Vi, and current shunt is I0 upon II, where I0 is the output current, II is the input current. With feedback, For voltage series, the gain will be V naught upon Vi, right? Voltage shunt V naught upon Ii. For feedback, Vf upon V naught, and you can see for feedback If upon V naught. For current series, feedback will be V naught upon I naught, and for current shunt, feedback will be If upon I naught. So gain with feedback for voltage series is V naught upon Vs. Now that is the Vs is the applied voltage. Vs is the input voltage and V naught is the output voltage. So voltage shunt is V naught upon Is, and current series I naught upon Vs, and current shunt I naught upon Is. The voltage series feedback connection with a part of output voltage feedback in series with the input signal, resulting in an overall gain reduction. If there is no feedback, if feedback is zero, the voltage of the amplifier stage is V naught upon Vs, that is V naught upon Vi. If feedback Vs is connected in series with the input, then Vi is the difference between the input and the feedback voltage. So substituting the values over here, we can get the overall gain with the feedback V naught upon Vs. This is nothing but A upon 1 plus A into beta. It shows that the gain with feedback is reduced by the factor 1 plus A beta times, where A is the forward gain, beta is the feedback gain. So this factor will be seen to affect the input and output impedance of other circuit. So voltage shunt feedback, the gain of the network V naught upon Is, and V naught will be given A into I, and substituting all the values, you can see that the gain is. Now here it is, voltage series feedback is shown. This is the forward network, this is the amplifier, and this is the output part, and connected to the input. So you can see A is V naught upon Vi, beta is Vf upon V naught, and Af is V naught upon Vi with 1 plus A beta times, that we have seen already. So voltage series feedback, the voltage series provide sufficient circuit detail to determine the output impedance with feedback. The output impedance is determined by applying a voltage Vs, resulting in a current Is with Vs short circuited, that is Vs is equal to 0. So the voltage V is then V is equal to I into Z naught plus AVI. For Vs is equal to 0, Vi is equal to minus Vi. So this can be written, and rewriting the equation A plus beta AV is equal to I Z naught. So when we solve for the feedback impedance, you can see V upon I, it comes out to be Z naught upon. So you can see the output impedance for voltage series feedback is reduced by the factor 1 plus A beta times, that is without feedback, without feedback, Z naught upon. So here is a summarized table showing the input impedance and output impedance for voltage series, current series, voltage shunt, and current shunt. We can see for voltage series, the input impedance has been increased by 1 plus A beta times. Current series it's also increased by 1 plus A beta time. But for voltage shunt, the input impedance has been decreased by 1 plus A beta time, which is not desirable. And for current shunt also, input impedance is decreased by 1 plus A beta times, whereas we require high input impedance for cascading purpose. So the output impedance should be reduced. Ideally, here you can see for voltage series, it has been reduced by 1 plus A beta times. For current series, it has increased, which is not desirable. Again, you can see for voltage shunt, it is decreased, and for current shunt, the output impedance is increased by 1 plus A beta times. So this is the all 4 configurations of feedback network, and you can see the change in input and output impedances with respect to the feedback elements. So here is an example. Determine the voltage gain, input and output impedance with feedback for voltage series, which is having open loop gain is minus 100, input impedance is 10 kilo ohm, R is 20 kilo ohm. For beta is equal to minus 0.1 and beta is equal to minus 1. So using the equation for the voltage gain, you can see A upon 1 plus A beta time. We substitute all the values and we have got the overall gain minus 9.09, and we know that the input impedance for voltage series is 1 plus A beta times the input impedance. So we substitute the value of 1 plus A beta and we get 1 at 10 kilo. And output impedance is decreased by 1 plus A beta times. So Z naught upon 1 plus A beta, we get this way. Similarly, the same can be calculated for other value of beta. that is the feedback gain, minus not 0.5. We substitute again the same values over here. For gain A upon 1 plus A beta, we substitute the value over here, and for input impedance again 1 plus A beta times increased, and output impedance 1 plus A beta times decreased. So this is all about the full configurations of feedback network. Thanks for watching. See you in the next lecture. Thank you very much.